that. And in fact, we can kind of feel this here. You'll be able to feel it's even better with other data sets. But let me go ahead and reload here and go ahead at the same speed as we were before, choosing merge sort. Let me fit it onto the screen at once. Actually, you should speed it up to the original. So what is it doing? It's using a bit of extra memory, just as we were on the screen, using some additional space. But notice as it does that work, it's kind of moving things back and forth. And it's actually saving space. Even though I used log n amount of memory by keep moving it, this was stupid. Like, I didn't need to keep using more memory, because I wasn't using the stuff anymore above. So with merge sort, you really just need twice as much memory as those other algorithms, because the first time you need to move them here. And then, even though I did it visually, deliberately to move it to yet another location, just keep moving things back and forth as needed. And that's what's happening with that algorithm there. It's not quite as clear to see with this visualization. So let me open up this other one here. Now go. And you'll see merge sort all the way on the right. Done. All right, so insertion sort got a little lucky here just because of the order of the elements, and the size of the data set isn't that big, which is why I wanted to show the other one. But if we do it once more, you'll see again that merge sort is pretty darn quick. And you can see it doing things in halves, and selection sort and bubble sort are still doing their thing. And if we did this using not like, what is that, 10, 20 bars total, but 100 bars or 1,000,000 bars, you would really, really feel the difference, just as we did with the phone book example as well. Any questions there on that? And we won't walk through the code, but if you're curious to actually see how some of these ideas map to C code, you will find in the CS50 appliance in the source code from today a couple of files, binary 0 and binary 1 in linear.c, all of which implement binary search and linear search in a couple of different ways if you actually want to see how those map. But what we thought we would do in our remaining time today is tee up one of the next algorithmic challenges. It turns out that there are wonderful opportunities in computer science to intersect with other fields, among them the arts and very specifically music. And it turns out that music, whether you're an audiophile or even a musical theoretician, there are relationships among the sounds that we hear and the rate at which we hear those notes, which is to say they follow patterns. And these patterns can be produced by computers. They can be generated by computers. And what we'll do ultimately in problem set 3, in fact, is introduce you to a bit of the musical world, whether you have some prior experience or not. And Brian, if you wouldn't mind coming up just to assist with this teaser. Here are just a few keys from a keyboard, and here are 88 keys from an actual keyboard. And Brian will help us in just a moment with some of these definitions. But you'll see here that there are 8 keys, or 1, 2, 3, 4, 5, 6, 7 white keys, and 5 black keys on the board. And it turns out that mankind, at least in Western music years ago, decided to standardize on how we describe these keys. And we assigned letters to them. And you might have heard of middle C, even if you've never played a piano before. And you might think of that as being the leftmost key there. And then it's D, E, F, G, and then A, B. And of course, on a real piano, there's keys to the left, and there's keys to the right. Do you want to play what C might sound like here? So that's C. And then if you want to, very well done. Do you want to go all the way up through the scale to B? It's kind of unresolved too, because what should have come next? That would be another C. And so what Brian's played for us is a full octave now, referring to 8, so C to C inclusive in this case. And those of us who kind of are familiar with music or like listening to certain music, you'll notice that certain things sound good, and there's actually mathematical and formulaic or algorithmic reasons that some of these sounds sound actually good. But what about these black keys? They are actually can be defined in a couple of different ways. And if you've ever heard of flats or sharps, Brian, do you want to explain what the relationship now is among the white keys and the black keys and how they sound different?
Yeah, sure. So a bit of terminology first. A semitone is just the distance from one note to the note immediately after that, both white and black notes included. And all it means for something to be sharp, represented by the hashtag or pound sign up there, is take a note and move it up by one semitone. So if we start with C and make that note sharp to C sharp, we move one semitone to the note immediately after it, which is that black note in between C and D. So that's C sharp. And likewise, if we had E sharp, that is one semitone or the note immediately after E, which in this case is the same thing as F. So F and E sharp are the same note. And in the meantime, flat is just the opposite of that. If sharp means move up one semitone, flat means move down one semitone. So if I have E, E flat is one semitone moving left on the piano keyboard.
And so even though a typical piano keyboard wouldn't be labeled as such, it does follow a pattern, and it does repeat to the left and to the right as well. And so as you learn to play piano, you learn what these notes sound like, you learn where these keys are, and you also learn ultimately how to read music, which might look like this. This is a familiar song, now officially in the public domain, and you'll see here that there are these little shapes called notes, or little circles, that happen to be on specific lines. And it turns out that if a note is on one line, it might represent the note A. If it's on a different line, higher above or down below, it might represent B or C or D or E or F or G. And if there's a sharp symbol or a flat symbol in front of it, that might off-shift it ever so slightly so that you're actually touching, in many cases, one of the black keys as well. Which is to say that once you have the vocabulary and you know what the alphabet is to which you have access, can you start to write it out, much like we write computer programs, but this is what a musician would actually see. And just to give us maybe a teaser of what you can actually do when you take into account the different sounds of notes and the different pace at which you play notes, can you give us a little something more than just a scale?
Sure.
So if you're a little worried what we're getting into, not only computer science and programming, but now music, I am absolutely among the least comfortable with this. And this is why Brian has kindly joined us here today. But it'll be fun, we hope, ultimately, to explore these relationships and also the intersection of one field with another. And to now tie these topics together, we thought we'd end by looking at a short visualization here, about a minute's worth of computer-generated sounds that give you not just a visual feel of some of the algorithms and others that we've looked at today, but also associate sounds with the operations of moving things, swapping things, and ultimately touching bigger and smaller numbers digitally. So here we have up first, insertion sort. Again, it's inserting into the right place the number. This now is bubble sort. And again, you can both see and now kind of feel all of the swaps that it's doing. We will get the satisfaction this time. This now is selection sort, whereby you go through the list selecting the next smallest element and plop it in its place. And the bars are getting higher and higher, just like the notes or the frequencies. This now is merge sort. And notice the halves that are developing. And this is by far the most gratifying sound at the end of this one. This is gnome sort, which we didn't look at, but very distinctly has a different shape too. It's not quite as ordered as the others. And that then are algorithms. And Brian will play us out for today. Otherwise, we will see you next week.